for being here. Today, I present our research, Dynamic Modulation Generative Observational Networks. The objective of this presentation is making high-quality synthetic GC-MS data using artificial intelligence generation model. So I hope this presentation will be bridging AI and chemistry more coherence. I'm presenter Namkyung Yoon and from Korean University. The content of presentations consist of introduction, method, evaluation, and conclusion. Recently, artificial intelligence, that AI is widely used as a tool for research on GC-MS data, such as detection, regression, or classification, whatever. But high-performance AI model needs a lot of high-quality data for proper training. So we propose DMGAN to generate high-quality synthetic data. In the GCMS in this research mean gas chromatography, mass spectrometry. GCMS separate and characterize components of chemical using each molar mass. The time in large peak is retention time, and other time in small peak is baseline time. This characteristic of GC-MS peak may confusing on existing AI model to proper training, because large variation between the peak of retention time and the peak of baseline time. The peak of baseline time is too small, and the peak of retention time is very large. So this make underfitting to training existing AI models. Then we propose a novel AI training method for these features of GC-MS. Our DMGAN is novel running methodology for GAN. This figure is structure of vanilla GAN. GAN runs adversely using two neural networks, generator and a discriminator. So then our DMGAN trains and generate individually by selecting peak in GC-MS through dynamic modulation technique. The dynamic modulation technique select peak at retention time as characteristic value and baseline time as non-characteristic value through k-mean clustering algorithm for GC-MS. This allows DMGAN to properly learn characteristic and non-characteristic peak without underfitting. Our DMGAN is implemented as follows. At first, generator is noted as G and discriminator is noted as D. G and D optimized with fully connected and convolutional layers. In addition, D use dot product attention mechanism known to be effective on GC-MS data. This is our previous research. Then in evaluation section, we present experimental condition. The GC-MS data of this research analysis of 2-chloroacyl acid sulfide with ethanol solvent. And we also develop a new 3D visualization tool to overcome the difficulty of seeing the GC-MS individually. Traditional tool of GC-MS tool seeing the individually, but our tool may put together, and we use Python code, so more high availability and low cost for modify to use. Then in evaluation section, we conduct performance evaluation by two ways. First, visual comparison with 3D tool show same characteristic peak at the same retention time. We can see the same characteristic peak in same retention time and non-characteristic time by versa. Then we conduct Pearson correlation coefficient to evaluation. Our DMGAN achieve high result GC and MS each. This result outperform than other models such as TimeGAN, DCGAN, VAE, and LSTM-GAN. These models sought for 1D signal generation model. At last, we present effectiveness of our DMGAN. The augmented synthetic data generated by DMGAN significantly improves the performance of classification deep learning model to identify 3 different chemicals, the mixture of diethyl methyl phosphonate, DMMP, and dispropyl fluorophosphate, DFP, and 2CES. At conclusion, our DMGAN effectively captures complex characteristics of GC MS data, and DMGAN generates realistic and diverse synthetic data for proper training. In future work, we will expand to more metric and more diverse chemical substance. I changed the PowerPoint to key focusing because I was afraid of time cap, but I did it too quickly. Thank you for listening.